I don't know what it's trying to tell me there, but I don't want it. There we go. All right, so let's see if this will work now. So when we do the chair flip for B, we wind up with something. There we go. That looks like. I always have to think about what it is. We're gonna wind up with, now this one is equatorial. This one is axial. So if it's 1,3 trans dimethyl, then there's no way we can get both of them in the more stable state. So we're stuck with one of them will always be in a more stable state, but there is no perfectly stable state or best stable state. So even though the cis configuration makes it seem like they're closer together, and one of the configurations puts both of the methyls axial, makes it the least stable way to have it. That also means when we do the chair flip, we get the most stable way to have it. All right, try the same logic with these two possibilities.
Yeah.
Okay, today's a hectic day.
Yelled at my dude in Connor. He's like, "You can't be in here cutting apples." I'm like, "My boss said I can be in here cutting apples, and I don't know who you are, sir, and I have the knife, so I'm in the ignore you."
Yeah, they need to iron out some kinks still with the use of the kitchen.
And then he's like, "I can set up your club table." And then he was like, yesterday, and then today he's like, "Go to set up your club table." And I'm like, "I have class. I've been yelled at by a stranger. I'm cleaning the kitchen. I don't know what's going on."
Don't stress about it. So we're gonna start with some review. Here's the plan for today. I was gonna see if I could try to get through all the new material in lecture and then use the lab time as exclusively as review then.
Right.
Except that we're starting with review and we're starting a little bit later than I wanted to anyway. So we're just gonna carry over. We'll take a break and we'll come to lab, and whatever lecture material we don't get through before lab, there'll be a little bit of that new material. But we have 3 hours to get through it and to review and work through practice.
Okay, beautiful.
Right, so we don't need to be stressed about time. I'm done being stressed about time at this place, so you two can be as well.
Awesome. Yeah, well, when my boss was late, and then we're like, "We don't know what we're doing. We don't know where anything is."
We're having fun. It's Halloween week, right?
Yeah, it's Halloween. Oh my goodness, I got to dress up for one of the hockey games. I had a flight suit, like a aviation suit. And one of the a family that I sit with, they have a daughter who's like 4, and she had a matching one. So we were both in our flight suits. It was so cute.
Fun. My oldest did that when he was 4. We found up an Air Force flight suit, and my mom lost her mind because her dad was an airman.
Oh yeah.
And he was the oldest grandchild. And so it was, everything at the time. But this year we found out about 2 weeks ago that my youngest knows the theme song to Ghostbusters despite having never seen the movie.
Oh my God.
And then we found a used Ghostbusters costume at the resale shop. So he's going, and so my oldest is going as Slimer. We've got him a Slimer onesie.
That's so cute.
So we get to see that at Trunk or Treat tonight.
Yay! I'm so excited for the Trunk or Treat. We're gonna have little DIY lava lamps for the kids to do.
Oh, fun.
I don't know what you're talking about. I don't know. No,
You can make edible ones too. Have you ever done that? You make Jello and then you shred the Jello and you put it into, for people of age, you put it in champagne. You make Jello shots and you put it in champagne, and the little shards of Jello go up and down with the carbonation.
That's so smart.
But you can do it with sparkling.
Oh yeah.
You have to mess with the densities a little bit, because if you're not making a true Jello shots, then they have a different density. But yeah, there's fun stuff with Jello with.
Interesting.
All right, so to catch you up on our logic here, Tim. We started with
And I tried to do the homework yesterday and I had no Wi-Fi where I was pet sitting, so I said, you know what, I'll use it as review tonight.
Okay. So here's where we started. If we wanna know which of these is more stable, we wanna look at which of these isomers is gonna give us the most substituents in the equatorial position. Because remember, equatorial positions, axial positions, these are the axial. If it's in the axial position, they're sticking straight up or straight down.
And equatorial is left and right or in and out?
Around. Think equator,
Right.
right? So the more of our substituents we can put into equatorial positions, the more stable that isomer, that conformer is.
Okay.
So for this one, the 1,3 trans dimethyl, the easiest way to draw it is both of them in the axial position, but then when we do a chair flip, we wind up with both of them in the equatorial position.
So this would be one like on the exam where I would bust this out and like play with it.
Yeah. You might even come with a cyclohexane already built.
Okay.
So that because it's gonna be cyclohexane.
Whether you like it or not.
It's the classic example that makes us think in 3 dimensions and hexagons show up all over the place, so.
I feel like, isn't it the most common, right? 'Cause it's the most stable.
It's the most stable of
So-
those,
Isn't it probably like the best one to know too? So it
Yeah.
goes up there.
exactly. And if you go to anybody who's taken organic chemistry and you ask them about the chair conformer of cyclohexane versus the boat conformer, they might get PTSD flashbacks, but they'll know what you're talking about. So for the second example,
So then how did you deduce A for the first one?
so A has 2 different conformers. One where they're both axial, but then that means that if we do the chair flip, they're both equatorial at the same time.
And we want the more we can put in.
Exactly. Axial is bad, is less stable. Equatorial is more stable. So isomer B, the trans conformer, we can put one axial and one equatorial, but if we do a chair flip, we still get one axial. There's no way to make them both equatorial for B. So that tells us that A is more stable.
And then
Because-
that is the one with more equatorial is this drawing, right?
Exactly. So these are both A, these are both the 1,3 trans isomer. But one of the conformers, I kind of like conformers because it makes you think transformers. At least it does me. One of the transformers
Mhm.
puts everything equatorial, even though the other one is less stable. So they're out of these 2 possibilities, this one's gonna be more stable. And for B, no matter what we do, one of them is axial and one of them is equatorial. Because we wind up with something that looks like. These are our 2 isomers.
And how do you know which one is the wedge and which one is the dash?
Practice. But basically, if we look at this. At this carbon right here. One of its bonds is in the plane of the board already. The axials are all in the plane. None of the axials are into the board or out of the board, because they all either go straight up or straight down.
Right.
So if
So our vertical is always a straight line.
vertical is always a straight line,
So then it's gonna be the horizontal that's either in or out.
correct?
And then if you look, it's just process of elimination then?
Basically, yeah,
And then, what is it, wedge is out or wedge?
wedge is out,
out.
Dashes are in.
So then like A looks like this. I have no hydrogens, ignore my no hydrogens.
Add one more carbon to it, but yes.
Can't, it's been the morning. I was like 1, 2, 3, 4, 5, 6. Yes, 6 carbons. No, 5 carbons.
Alright, so here's your. Let's make sure it's the way that looks most stable. So there's our form where they're both axial. This is
That is,
this one.
but that's the one we're given in A.
That's A, yeah. And then, but if you do a chair flip. They're both equatorial and they're pointing away
That's
from
a full
everything.
chair flip or a.
That's a full chair flip.
Sorry, wedges are into the board.
Wedges are towards you.
Wedges are towards you.
Think of it like
Which makes
if
sense.
it was a straight line, this is the end that's getting bigger. It's pointing towards you.
Well, and it's like a dot, dot, dot. Is the dashes, and that reminds me.
Dashes are behind the board.
It
yeah.
reminds me of the Star Wars intro.
Okay, yeah, exactly. It's a really crude geometric way of showing perspective. When you get used to it, it kind of looks like it's sticking out towards you, especially if I shade it in.
So then, how do you? The ones that we're drawing like this are only ever gonna be the cyclohexanes, right?
Correct.
Okay. So I was gonna say, how do you know when to draw it like that, but cyclohexane?
Anytime it's cyclohexane, the faster way to draw a cyclohexane is like this. But when you actually need to know about which conformer is gonna be more stable or axial versus equatorial, or actually show the 3D shape, it makes more sense
then-
to draw it as the chair.
Looking at it, how do you orientate it again so that it?
So start with the headrest and the footrest, and then make the arms go the way they're supposed to go.
Like this. And then. Flip it for your chair flip, but this did not move for some reason.
So when you do the chair flip, put the headrest down. And put the footrest up. And try to leave the arms where they are.
Where are these in the chair flip?
So if we're starting with them, I didn't bring my cyclohexane today.
It's okay.
So there is this conformer. They're both. Here's our chair or our headrest, our footrest, or our arm. Here's the footrest.
Ah, okay, so you would just look at it from the side.
The side, identify your arms and your head and your tail and look at it dead on.
Okay.
And then when we do the chair flip, you take the headrest, you flip it down. Now we're in a boat. And then you do the other side.
Okay.
So you flip the headrest down, then you flip the footrest up.
And what if we identify different ones as the head and footrest? Because we have it drawn flat first.
Because you pick which one's convenient. It doesn't really matter which one.
I had a waffle, an angled waffle.
We're just like little kids, Sean.
It's okay, I had leftover nerd gummy clusters from yesterday for breakfast, so.
It's
But I
Halloween.
fed the dog that I was pet sitting, so I'm.
There you
fine.
go.
Right, my kids are all fed. I made
Well,
peanut
that's what
butter and
matters.
jellies for dinner,
Perfect.
but
Is your wife not home?
she just has to get out the door faster because she has to be here by 8 and that
For dinner, or you mean lunch?
for dinner. Cause for trunk or treat,
Mhm.
for the kids, not for me. I still don't have any food planned, but
You could peanut butter and jelly it up too.
I probably will.
So you pick what's convenient. How do you know which one's convenient?
Usually the easier ones to visualize are the headrest and the footrest. And so I always put one of the things that I care about as the headrest or the footrest. And then the other one goes where it has to go. But I would never draw this one. It wouldn't be wrong, but I would never draw this one where the methyls are here and here, because that's making it tricky on myself for no reason. So put at least one of the things you care about at the headrest or the footrest, and it's gonna make your life easier.
Yeah, I voted it, or I chair flipped it, and it's not happy with me.
And it's not happy.
No, you did it, that's right,
Oh, I was looking at it here. Oh, yay.
because, and that's more stable, because what you did is you put both of those methyls are now in the equatorial position. They're pointing away from everything else, which means they're bumping into each other less. Right? So because you can't really tell, unless you have a lot of practice with this, you can't really tell which of these is more stable unless you do this. Because
Test.
a little bit, the practice test has one of these questions just like this.
If we both fail, will you curve it?
If you both fail, then we're gonna come back to the drawing board and we're gonna figure out what happens next. But
Right.
I'm not worried about that because
We're doing good, Tay.
We are?
Yes.
you'll be okay. Alright, so the only way to tell which of these is more stable though is to do this process, because that shows you that for B, both of these are B. In both cases, one of the methyls is axial and one's equatorial. There's no way to get to that perfect state of both of them equatorial.
And doesn't the hydrogens matter too when you're looking at these where those are who's interacting with hydrogen?
Anything, hydrogen's the smallest thing you can have attached to the carbon. So yeah, the hydrogens bump into the other hydrogens when they're axial, but that's better than anything else being axial. Since something has to be axial, having a hydrogen be axial is more stable than anything else, because everything else that you're gonna be working with is bigger than hydrogen. Hydrogens are tiny.
So on the next slide, when we're doing these, both of the wedges are coming towards us, right? But I can't get my 3D model to do that.
Yes, you can.
It is, because if you're looking at it from above, take your,
See, look.
Oh, so it's like this?
yes.
Okay. I did the wrong one first then.
What?
Okay.
Like this.
Let's see. Look like this. It's not. That's my foot.
Alright, so for this one, for A has two of the methyls on the same side of the ring and one of the methyls is trans to the others, right?
Yeah.
So I took this and I rotated it up. These two methyls that are axial are both above the ring, right? I took this one, I took this carbon and I made it the headrest. But that's good, that's perfect. Look, you made it, two of these are cis relative to each other and this one is trans relative to the others. They're not happy.
Too close. It's
They're-
like when we shared.
exactly, they're axial, but they don't wanna be axial. If we do a chair flip,
Flip it. Flip that bitch. Go up.
now this one's axial or equatorial. This one's equatorial.
No, they're happy-ish.
They're going, yay!
Two of them are happy, but the other one's axial now.
This one, the footrest.
Yeah.
This one's axial now. These two are both equatorial. I mean, but consider where the other position is, it's not perfectly axial,
Oh, okay.
but if the other one's definitely equatorial, right?
Oh, okay, so just like the other one.
Yeah,
So two are happy, one's not happy.
But
Okay.
we'd rather have two happy.
But
We'd
why
rather have two
don't
happy.
why don't we try the other one?
B, if they're all cis, is there a way we can make it so that they're all equatorial at the same time? Cause if so, that's more stable.
Yes. Okay. So we have. When it's like this, they're all too close,
Good.
too friendly, we're not happy. And then we do this.
Do they all go out?
And they're all equatorial once you do the chair flip. If they're, anytime you do a chair flip, everything that was axial becomes equatorial. They always swap when you do a chair flip.
Now it goes yay. When
And
it
now
goes
they're,
yay, it's happy.
exactly.
Yeah, we always want to.
So which of these isomers can be more stable than the other?
B.
B can be more stable because one of its conformers has everything equatorial.
Wait, hold on, let me try to draw this.
So, but if I wanted to like redraw B through in my chair, and I wanted to draw them all with lines going straight up or down, and then in the next one show that they're all going out, would that be okay with just straight lines instead of
That's
the
perfect.
wedges and dashes?
So the wedges and dashes are helpful. And I always find it because the axial is always straight up and down, which means it's easier to identify where it is. So for this one, all of them in the axial position is gonna look like this.
Right.
And when we do the chair flip now. We get one out that way,
Yeah.
one's out this way,
Yeah, and then one's going.
and one's going into the board away from us. So they're all equatorial. I'm pretty much always start,
So it's an equatorial, always a dash or a wedge.
except for the headrest and the footrest.
Because
Yeah,
they
you
don't
want
go, they don't
rules.
go in and out at the headrest.
Because the headrest and the footrest already have one bond coming out. And one bond going away.
Okay. They didn't for no reason.
The reason is to convey as much information as possible, as simply and universally as possible. Because you really don't want to rely on chemists' artistic skills.
Then why are we having them draw things in random shapes like this?
Well, because this is an easy shape to
Did-
represent the 3D model.
No, a hexagon
Is
an
not
easy
3D,
shape.
is not 3D, and you didn't think it was easy when you first did it.
Okay, so this, I drew this.
Yeah, you got it.
Okay, great. Do I have to put my H's on for you?
No,
Okay, great. I hate them. I'm gonna break up.
and now you're close, you're becoming an organic chemist. Organic chemists hate drawing
I'm like,
hydrogens.
hi. There's so many of them and we all know that they're.
We're all know, exactly. This is a rite of passage. You have to get to the point where you can count to 4, but not 5.
I've been hitting, my H's have turned into like X's, cause I just go really fast, I'm like, meh.
It's
There's an H.
not unusual. So there are organic chemistry classes where you have to take your first midterm and not draw a single carbon with the wrong number of bonds before you're allowed to draw skeletal structures. Because we don't trust you to count to 4, but not 5. I trust y'all, so we're not doing that, cause I also don't wanna continue drawing my hydrogens.
Because then you also have to count all of our hydrogens.
I have to count all of your
right?
hydrogens.
I'm also pretty used to counting to 4. You are too, for.
I think we're okay with
I
that.
count to 8.
I count to 4 with horses. You count 4 strides and you reset. 1, 2, 3, 4, 1, 2, 3, to make sure I'm on the same pace.
Music's the same way, right? Everything is based around
That's a
a 4
trick.
count.
That's a trick
Yeah.
she uses sometimes. She's like, you're thinking too much. Just sing a song. And I'm like, okay.
It's gotta be the right song. Don't
like-
sing a 3/4 song.
She's like, I
Yeah.
can't hear you. And I'm like huffing and puffing and trying to sing.
It's actually really funny. I should come
It's-
to your practices.
You should. I'm hearing counting. I'm like, you're 100 feet away and it's windy.
Project.
Project?
You gotta project.
Oh, yes. I'm also
Oh.
trying not to die.
All right. So new skill, switching away from cyclohexane.
Great.
We're assigning right-handed versus left-handed. So we're going to chirality. We're talking about what are called enantiomers, which the word is underneath the title there. enantiomer. An enantiomer is an isomer where the mirror image is not the same. So it's basically one of the pieces, the right hand versus the left hand, if you have chirality.
Yeah, so wouldn't an enantiomer, you saying an isomer where mirror image is not the same, wouldn't that just be a chiral mirror?
Exactly. So an enantiomer is one of the chiral, one version of the chiral molecule is an enantiomer. Oddly enough, I don't know the root for that, but I guess it has something to do with mirror in Greek.
Chiral or enantiomer?
Enantiomer. Alright, so the trick with enantiomers, anytime you have 4 different substituents attached to a carbon, then it's chiral, right? We learned that the other day. We spent some time with that. So how, just like with cis versus trans, we needed new vocab to be able to say, oh, they're on the same side versus on opposite sides of the ring, right? We're gonna do the same thing, something very similar here. We're adding a new thing to our nomenclature to specify which enantiomer are we talking about. Is it the right-handed one or the left-handed one? All right, and so the two versions, they call them R versus S.
When you say right and left, wouldn't it just be like original versus mirrored?
So which one's the original? That's sort of arbitrary, right?
But that's like basically what we're assigning that to.
Yes. Right, so if I just say that you have dimethyl cyclohexane, it could be cis like this one, or it could be trans, right? We needed to define what cis and trans were before those words meant anything, before we could describe this version versus the other version, right? That's the same thing we're gonna do here.
Cis means straight, trans means flipped.
Trans means across. Right, so this is cis.
Oh, and it's where the methyl groups are. Those methyl
Exactly,
groups are
relative
cis.
to the ring.
And if it was just one carbon over to the left, it would be trans.
It would be
No, if it was into the board.
exactly. So that's cis. That's also cis, because that's the same molecule flipped over. If one of them is flipped, then it's trans. Because now to get from one to the other, you have to go across the ring. So when we're doing this with a tetrahedral carbon, we have to have a better procedure for it, because now we're dealing with 3 dimensions. With cis and trans, we're really only looking at 2 dimensions, right? It's either above or below. In this case, it's a little bit like looking at something and assigning, is that somebody's right hand in a picture, or is that somebody's left hand in a picture? Easy once you have the practice for it, but we need to do that at the molecular level. And so the way we do that is we assign priority. And priority is easy. Priority just goes based on atomic number. Whatever has the largest atomic number has the highest priority. And if there's a tie, you go one step further out.
What do you mean?
We'll do some examples in a second, but let's practice with this just with random colors. So let's say we assigned priority in this figure. The red was the highest priority, it had the highest atomic number. 2 was next, then there's 3, and then there's 4. If we want to assign whether this is right-handed or left-handed, once we assign priority, we're going to take this object and we're going to rotate it so number 4 is pointed into the board. So we're going to take it and put number 4 into the board because it's the lowest priority. And we have to, we're basically saying that whatever is the lowest priority is the bottom of the molecule. So we're gonna take it and turn it so that the bottom of the molecule is facing away from us. We're looking at the top of the molecule. And then you just count 1, 2, 3. And so the trickiest thing here is rotating. So basically, to go from the way it's originally drawn to put number 4 away from us, we had to take this object, pick it up and spin it. And usually there's more than one way you can do it. In this case, you can picture picking it up by number 1 and twisting it. So number 1 stays in the same position and everything else spins like a fan blade. So that takes number 4 and puts it where 3 was, 3 moves over to 2, 2 moves over to 4. So all 3 of those rotated. Once you get number 4 pointed away from you, and we're looking at the top of the molecule, you start at 1 to 2 to 3. And you just draw a circle. And when you draw your circle, it's either going to be clockwise or counterclockwise.
Why are we drawing a circle again?
Because that's how we decide whether it's right-handed or left-handed, is we put number 4 pointed away from us. And then we count 1, 2, 3.
From right to left?
From 1, and it'll either go right to left or it'll go left to right. In this case, when I drew the arrow 1 to 2 to 3, it was clockwise, right?
Yes. But how do you know that's the way you draw the arrow?
Cause that's.
You always count 1, 2, 3.
Yeah, you're not gonna go 1 through 2.
If it was the opposite order, if I drew this and it was 1, 2, 3 like this, then my arrow would be going the opposite direction. If you draw your arrow clockwise, that's right-handed. If you draw your arrow counterclockwise, that's left-handed. Fun fact that I never lose an opportunity to point this out to my left-handed brother. The Latin word for left-handed is sinister.
So clockwise is.
I was wondering why
Right.
it was an S.
The clockwise is right, like righty-tighty, lefty-loosey. So let's do some practice. It's always assign your priority. Put number 4 pointed away from you. Count 1, 2, 3. So let's start with this middle one first,
Okay, the simple one.
the simple one. And I'll even draw the H on there in the correct, with the wedge drawn for you.
So it's assign priority, turn number 4 away from you. And then draw your arrow.
And then draw your arrow. And it's either gonna be a right-handed arrow or a left-handed arrow. When I told you that chemists get particular about their arrows, you had no idea.
No. Didn't realize there was even more.
Not much. Big fly, so picky about your damn arrows.
So chlorine is gonna be our 1, right?
So we're looking, so when we do this, are we isolating just like one central?
Basically, we're looking at one carbon. We're looking at the chiral carbon. This is why we did that assignment the other day. The quiz was, where's the chiral carbon? So I suppose that's step one. Before you can assign priorities, you gotta figure out where your chiral carbon is.
But then our chiral.
Step zero, call that step zero.
Our chiral carbon, does that one get a number or is it just the branches that we know?
It's the branches attached to the chiral carbon.
Okay.
So Taylor, you're not the only one whose H's started looking really questionable.
I just like stopped picking up my pencil, cause like, what's the point? What's the point? Just adds to money.
Very existential of you.
She's such a pessimist sometimes.
We've all been there.
Not big enough to decipher your big grammar.
All right, so first step, we figured out where the chiral center was and I redrew it blown up.
Right. Yes.
So now we have to assign priority. So out of these four things, what's gonna have the highest priority?
The chlorine.
Chlorine. Priority one. A lot of times, the easiest thing to find is priority one and priority four.
The hydrogen.
Hydrogen's gonna be 4. Then we have a tie. Right, because the first atom that we get to from our chiral carbon is another carbon in both cases.
It doesn't matter that that one has more on it.
Or
It
H's.
is,
It's a
it
longer
will,
one,
but
it's a longer one.
let me redraw it, the whole thing. It's gonna help in the long run. You don't have to redraw it necessarily. If there's a tie, you always take one step further out.
Oh, so since that one on the right doesn't have another step out.
Its next step out is a hydrogen.
So it would be 3.
So that would be, that would be priority 3. The other direction is gonna be priority 2 because
Yeah.
you take a step out, you hit a carbon, we're tied. Take another step out, we get hydrogen and a carbon. So the fact that we went carbon, then another carbon tells you that's higher priority.
Now I'll move it.
Now we're gonna have to move it. So for moving it, it can be helpful to, now that we assign priority, forget about drawing the propyl and the methyl and just use the numbers. And if we redraw this, then we get 1, 4, 3, 2, and that's a lot easier to redraw or to rotate around in your head. So there's plenty of ways, there's a lot of ways you can rearrange this to put number 4 into the board. What I find the easiest is to rotate 3 of them, like a fan blade, like we did on the last one. So we want 1 to go or 4 to go where 1 is currently, right? So those 2 both have to move. So pick either 2 or 3 and hold them constant. and we're gonna do that. And it doesn't matter whether you hold 2 constant or whether you hold 3 constant. In this case, the way my hands are right now, my middle finger is 1, my pointer finger is 4, my thumb is 2. So if I wanna put my pointer finger where my middle finger was, I spin it that way. And I've had people do things like write 1, 2, 3 on their thumb, pointer, middle finger. Because that'll always, you can always use that approach.
Yeah. So then 3 would be your arm staying constant?
So then, yeah, and then in this case, 3 is my elbow or my wrist, however you wanna visualize it.
Yeah.
You use your other hand, then 2 staying constant. I'm rotating the other 3.
So then we have 4 going back.
Wait, I can't get this to be that. Like this?
What's what? Well, then you don't wanna hold your purple constant, cause your purple is going back. You wanna hold either your green or your yellow.
No, my purple's going forward right now, like at first.
But you don't wanna hold this and move everything else. You wanna move this.
But I'm trying to get
And
this to
move
look
that
like
and
that.
that. So. That's what that is. And then if you rotate it. If you.
Stayed nothing. Oh, the red stayed still.
What? Nothing is staying still.
So in this case, the model actually, it helps visualize what's going on, but unless you can be really careful with keeping 1, 2, 3, 4 straight, it might actually. It might actually hinder a little bit. It's easy to mix up the random colors, right?
Yeah.
So in this case,
Well, I mean, I assigned them in my drive
okay, good. Then as long as you can keep them straight, that should work.
and I just put them in rainbow order.
Perfect. Then in that case, you just take number 4 and put it away from you. You don't need to worry about,
But nothing, like nothing's holding still. If I do that,
doesn't matter
okay.
if you've actually got the 3D, what's number 1, or no, what's number 4? So you put number 4 away from you. So it doesn't matter whether everything else stayed constant or not if you have a 3D object. If you're trying to do this entirely on paper, it's a little trickier to visualize. But all that really matters is that if 4 is pointed away from you, you count 1, 2, 3.
That one was
Oh.
now going towards me.
So you went in rainbow order, you said, right? So red, orange, green then? Be 1, 2, 3. 1, 2, 3.
Does it matter
Clockwise.
which one is pointing towards me at this point?
No. You just count, once you get the priority assigned.
So for that one, we're gonna go clockwise, right?
We count 1 to 2 to 3. It's clockwise.
Which is
R. So this one, we would, if we were naming this middle molecule.
Yeah.
Say it's pentane. It's 2-chloropentane. That's all review. We're comfortable with that, right? And then we just say because it has a chiral carbon, we have to specify what the chirality is. What is which enantiomer are we looking at? And so we just say R, R2-chloropentane.
Okay.
And we're just naming the rotated one?
Just, it's the same molecule, we just spun it around.
Why are we naming? Well, so now that we know that it's an R at the front.
If you
How
don't,
does knowing, oh, so it just adds a
It just
letter,
adds to the
another
word.
letter.
Right.
Okay.
you can see a picture of somebody's hand in a picture, in a photograph and say that's a hand. But it's not, what is it, somebody's right hand or is it their left hand? Until you assign right-handed or left-handed, you don't know which version of it is it. Which seems like something we don't really care about, but we do care about it in terms of biochem. Because we had that thalidomide example the other day, right? It turns out, and in fact, there's you can buy methamphetamine at the grocery store. You can buy the left-handed version of it.
Which is,
It's not cold medicine.
It's called lead methamphetamine.
oh,
It's not the version that is psychoactive. Right-handed methamphetamine is the one that gets you high. Left-handed one works as a decent nasal decongestant. And so we care about chirality and whether it's right-handed or left-handed for most of the applications where we care about that are in biochemistry because enzymes are three-dimensional and their active sites are three-dimensional.
does it matter if you take the left-handed and the right-handed version of something at the same time?
It can, because they're gonna have different effects,
But they won't affect each other.
not
After I
necessarily.
watch room, I'm on ADHD meds and I can't take Sudafed.
Cause the methylphenidate for my ADHD meds reacts with my Sudafed.
That it's the same enzyme that's responsible for breaking both of those down. So you compound,
But that's not the other version.
I'm on methylphenidate.
no, it's a different methylphenidate versus pseudoephedrine are two different drugs. They're interacting with each other. Drug interactions, it can be mirror images interacting with each other, but more commonly, it's because the same enzyme breaks them down.
Got it.
And if the same enzyme breaks them down, you basically gum things up by having both of them present at once.
Yeah.
I mean, the only thing is my ADHD meds don't work as much. Sometimes if I'm really sick, I'm like, I don't care. I'm dying.
It'd be a little bit like trying to, if you are the enzyme trying to break down both of these things at the same time, be like trying to take a calculus test and an OChem test at the same time. It's doable, but you're gonna be a little bit less efficient at both of them, right? All right. So we don't actually have the way, haven't learned how to name these yet, alcohols yet. So we're not gonna name that right now. We're just gonna assign priority and figure out if is it R versus S.
But don't you just do an O?
No.
We
We do, but I'm not testing you on that, so we're not gonna get into it right now.
We learned that in.
Yes.
I'm getting chocolate on my jeans. I gotta look no, after.
We'll do this one real quick, then we'll take our break, okay?
Okay.
Man, on you.
No, it's just me being messy.
So these ones already have chirality assigned.
This one makes it really easy, as it makes it harder to figure out how many total carbons there are. So actually getting to the final name would be trickier. Because it's already done part of the work for you. So now it's just assign priority.
Tricky with that.
It's not chlorine. Which one are you working on? Oh. I'm wrong.
Are you gonna give us lots of space on the test to like work through all of this?
Yeah, I'm only gonna print it one-sided,
Oh,
And
so
I'm
we'll have
gonna-
the backs.
so you'll have the backs and I'm gonna try and spread them out, so it'll look like it's a big old booklet, but
Right.
that's so that you have lots of white space.
Thank you.
No problem.
And what the bigger atomic number, the more priority, correct?
Bigger atomic, and it's not like you sum up the atomic numbers for the entire branch. It's whatever's directly attached you look at first. So even though bromine is bigger than oxygen,
Oxygen is bigger
you
than
hit the
oxygen.
oxygen first. I remember this slide.
Still clockwise.
Still clockwise. And that's what I'm remembering, is I happened to pick 4 examples in a row that all are R. Purely by chance. But the process doesn't change, your last arrow would be drawn counterclockwise
Yeah.
if it was S.
So, I mean, really, they're not that bad to rotate as long as the 4 is one of the ones on the bottom that can just twist. But like the first one is a little difficult, I feel like, because the 4 is kind of up.
This one's 4. Oh, you mean this one was?
Yeah.
It's all just a matter of perspective anyway. It just takes some practice to be able to see it.
Yeah, that's true.
Because the other thing you can do with this first one. So it was 1, 4, 3, 2.
Yeah.
The other thing you can do with this one is if 4 is sticking straight out towards you, then you're looking at the back side of the molecule, right? Instead of the top front of the molecule.
Just like,
You can just flip the whole thing. Or the other way that I think about it is, well, what if you stepped through the board and looked at it from the back?
then it would just, you wouldn't even need to switch it really.
Right.
You just need to say that.
You can move your point of view instead of the molecule. Moving them, that's really what you're doing by moving the molecule, is changing your point of view anyway. And this is why visualizing it in 3D, while it takes practice, is really valuable, because the sooner you're able to see these 2-dimensional drawings as 3-dimensional objects, the faster this all goes and the better point of view you have with it. So I can look at this, if 4 is coming right out towards us, I can go, oh, that's 1 to 2 to 3, but I'm looking at it from the backside,
Right.
it's still R. And you can even do something like, okay, I'm going this way, 1 to 2 to 3. And
Yeah.
so it's looking at the backside of the clock, right?
Yeah. Okay.
Or it's looking at the bottom of the screw instead of the top of the screw. Takes practice. This way will never let you down.
Yeah.
It just takes a little bit more practice to get from here to putting 4 in the back.
did we name it? No.
We did not name
No,
it because of the alcohol. So the skill we're really adding today is R versus S.
And the one on the right is an R.
One on the right's an R, and I believe if I'm remembering correctly, this one's an R too, but that's just on accident. I didn't mean to pick 4 R examples in a row.
No, I just asked.
But we didn't do it all one. No.
All right. Let's take our break. We'll come back. We'll do the third one here. And then there's 2 more little caveats for how we think about these that we're gonna add. And then we're gonna talk about energy.
Cool.
And at some point in there, we're gonna take a lunch break and come back and do it in lab.
Do you want us to actually move down to the lab or do you want us to just come back in here?
I'm not sure if this room is open after.
I think it is. Oh, no, it's not, because normally after club, there's people coming in. Oh, no, that's on Thursdays. I don't know.
We'll just go down to lab, or we can, once we finish getting through the new material, we can hang out in the common space down
Oh,
there anyway.
Cool,
So,
because I don't
but
like.
either way, let's come back at quarter after.
Yep,
We'll do a little bit more lecture and then go from there.
sounds
And
good.
then, did you tell SAS I can have my molecule?
I did.
I didn't
Micah
have
made a
my-
note. She made a note. But if she doesn't remember, jog her memory, have her call me.
She's not even here, we're good.
She's sitting like so soft, we're ready for it.
What if we start lecturing to like an empty classroom, he walks in?
And say what? My brain is melting and on fire. And frozen. How is this possible? Let's look.
So yummy, huh? There he is.
my turkey bacon?
No, it's okay. I'm not gonna take your, food. I'm okay,
I
actually.
mean,
She doesn't eat meat and I don't want it.
well, what's about the track?
What'd you give to Sue that one time? She was so happy.
A sausage patty?
All right. Let's look at, well, that's actually pretty good.
Sure.
If you're into that sort of thing. Let's do the first one. And we'll actually name this one all the way through. Because that's gonna be good. That's gonna be good. Well, since it's already written this way, we'll start by figuring out R versus S. And then we're gonna go from this structure to skeletal structure so we can do the full name.
Okay.
All right. So a point about assigning priority here, though. Because we got an interesting tie here.
Okay.
So for the one that goes straight up and the one that's into the board and to the right, they both go. Your first step, you get a carbon. So tie.
Yeah.
So we take another step. Both carbon. So we take another step. Both hydrogen. So it looks like a tie, right?
Wait, how do you draw the one that goes up with the, because of the parentheses is confusing me.
So that's an isopropyl group. It's a carbon with a methyl here and a methyl there.
So then you don't even count the methyl, so that you just count the H.
Well, so as far as assigning priority, you always take the steps towards the biggest thing. Here, though, we go carbon, carbon, hydrogen, carbon, carbon, hydrogen. So it looks like a tie, but it can't be a tie because they're two different substituents. So basically, you do it again and you say you have to take a different route. If we have to take a different route for your next steps, it goes still carbon, so it's still tied. There's a carbon that's a different carbon. So this one gets higher priority.
What?
Because it's got a branch and it's not just repeating the same carbons.
So that one's number 2.
So that means that the isopropyl group, the methyl ethyl group is number 2.
She's lying. And how did you
Sorry.
get there again?
Because we have to go a different route second time we do it. And the different route gets us to another carbon that we hadn't touched before. So that gives us a priority.
But on the other one, we don't have it.
And on the other one, it's just a straight ethyl group, there is no other carbon for us to go to. All right. So That's just finer points of assigning priority. Once we assign priority though, then it's just a matter of rotate, put number 4 into the board or move your head. So 1, 3, 2, 4. So we're gonna take number 4, which is my thumb. And we're gonna rotate it so it's in the back. So that leaves 2 where it is. 4 is in the back, 3 comes forward, 1 moves to the left.
And it is.
As I remembered. Getting back to give you 4 R's in a row. Did you choke on some sausage?
No, I inhaled and sipped at the same time and it didn't go very well.
Alright, so let's finish, so it's R. Let's redraw this whole thing though as a skeletal structure so we can actually name it, because that's the last step here.
How delicately holding 3D structure.
I need to look at it. My fingers are too fat.
So just redrawing it as a skeletal structure. We can kind of start to see where our longest continuous carbon chain is gonna be.
Wait, we're drawing the original from skeletal structure or the turned one from skeletal structure?
Either way, should give us the same answer. I started from the original because that's just what I'm looking at. But we should be able to count 1, 2, 3, 4, 1, 2, 3, 4, 5. I think that there's a way 1, 2, 3, 4, 5. We can get a pentane. And attached to, there's a methyl there. There's a methyl there and a bromomethyl. So this redrawn looks like this. But you notice, even though this is a chiral carbon in the middle now, I'm not worried about showing out versus in because we already assigned it as R. So that means we can draw it however we want in order to make it easy to name it. Now we can say, okay, well, there's our pentane. And we've got 2, 3 dimethyl. And then we actually do have a complicated branch.
So we.
So 3 bromomethyl, 2, 3 dimethyl pentane.
Did you get from drawing it one way to drawing it the other way?
You just broke it down.
So this, I took this as it's given. and I redrew it as skeletals without any of the hydrogens. And then I said, okay, I think the longest chain I can get here is 5 carbons in a row.
And you just kind of like. froze
So
it.
then I said, okay, if it's 5 carbons in a row, I'm just gonna draw pentane and then I'm gonna add the branches where they're attached.
That's why I was getting through the homework when it was all like complicated, almost overlapping. I broke it down like that.
Yeah, it's not gonna, it'll never let you down to just look at it, count your longest carbon chain, and then see what's attached where. And then final step. R, 3-bromomethyl, 2,3-dimethylpentane. For whatever reason, the R and the S are traditionally put in parentheses. Doesn't really matter as long as they're capitalized.
Okay.
So it's a new skill for figuring out R versus S.
Yeah.
And procedure that you have to remember. But if you just break it down as assign priority, put number 4 away, and then it's either clockwise or counterclockwise.
I'll be allowed to have a periodic table.
Yeah, you'll have a periodic table.
You'll give us one.
Yeah. Just, I'll give you that one. Just staple to the back, fresh one.
Cool.
And really the putting number 4 facing away from you is a little bit like putting the point of the screw into the board. It's hard to know the right way to spin the screw unless the screw is pointed the way that you're used to thinking about it, right? That's all the rotation step is doing, is putting it so that the point of the screw is down and then you can see 1, 2, 3.
Yeah.
All right, last piece about stereochemistry for now. If you have 2 chiral carbons, also, and chiral carbons are also called asymmetric centers.
Okay.
2 asymmetric centers, each one of those asymmetric centers has an R and an S. Which means you can get up to 4 stereoisomers. Right, because in this example, if you have 1R, 2S, if you flip both of those to their mirror image, you get 1S, 2R. So to go back to the hands in a photograph analogy, if you only have one person in the photograph, the hand is either a right hand or a left hand, right? But if it's 2 people in the photograph, you could have 2 left hands, 2 right hands, a right and a left and a right.
Yeah. That's
all this is showing, is that there's 4 possibilities. Right, because then you can have 1R, 2R, 1S, 2S. But these are enantiomers. 1R, 2S. If you flip both stereo centers, you get 1S, 2R. If you flip one of the stereo centers, that's not an enantiomer because it's not a mirror image. Correct, yeah. The reason that we use both of those terms is that you can have stereo centers that are not chiral carbons, like cis versus trans. Cis versus trans is also a form of stereochemistry that's not necessarily a chiral carbon. But that's a separate thing. I just want, for now, we're just gonna use the terms interchangeably, chiral carbon asymmetric center or stereo center. All right, so if these are enantiomers because they're mirror images of each other, and these are enantiomers because they're mirror images of each other, what are these relative to each other? they're not mirror images. One's trans and the other one's not. We don't want to use that same term though, because then that would get confusing. Because we've already used that term.
New term you're about to tell us.
Yes. They're
Wow.
diastereomers. I might have actually. In di, because two stereocenters means that you can have diastereomers. So they're stereoisomers of each other that aren't mirror images. So how do I test you on this? Basically, I'm gonna ask you, are these two drawings the same molecule, enantiomers, constitutional isomers, meaning things are actually attached in different places, or diastereomers? All right, so, and that's on the practice test too. Has some examples. Basically, this A has 3 stereocenters. Right, there's a chiral carbon, there's a chiral carbon, there's a chiral carbon.
Right now that we're just looking at chiral carbons is a stereocenter.
Yeah. So if it's got 3 chiral centers, 3 chiral carbons, if it's an enantiomer, all 3 of those have to get flipped.
Right, they're not.
They're not all flipped, only 2 of them are flipped.
If it's an enantiomer,
If it's
so
an-
it's a diastereomer.
So these ones are diastereomers. It's not the same molecule. It's not a constitutional isomer because everything's still attached to the same atoms, but they're just arranged differently in space. But it's not a full mirror image. If it was a full mirror image, all 3 of these would be flipped. So if this one was flipped, now they're enantiomers.
Right.
The trickiest way I can do this is to make it not entirely obvious. By rotating things around, putting things in different places.
But the bonds also still aren't, only one of them is flipped.
So this one's definitely flipped.
Yeah.
Is this one though? Because if we took this molecule, if we put this big long carbon chain back where it was, we'd have to rotate it twice, right? Rotating it once would put the methyl into the board, the hydrogen would go where the methyl is, and this would be coming out of the board. And then if we rotated it again, we'd wind up with the methyl out of the board, the hydrogen into the board, and this back where it started.
So to reconfigure this to the way it was before,
Exactly.
would the best way to be look at it in 3D?
Yes. Mentally or build the structure. Because if you do that, you end up seeing that this molecule on the right looks like this. Which means it is an enantiomer. It doesn't look like it because I didn't do it, I grabbed this out of a textbook,
Right.
but because this problem has it twisted around the other way. So it's not obvious, the foolproof way of doing it is to actually assign R versus S for both of them. Because if you can look at this and say, 4 is coming out of the board, 3, 1 and 2. 1, 2, 3, 4 is coming out of the board, this one's S. And this one's gonna be And so, and then you can look and say, okay, well, that's S and that one's R, because it's flipped. If you do the same thing for the second stereo center, you could see that they're both got flipped. Takes a little bit more time to do that. And the way that it's written on the practice test is really pretty close to how I'm gonna do it on the test. I won't promise that they're not, that the clues aren't used twice, but it's basically multiple choice.
So we're looking at
We always mirror it, yes?
like the way you're giving it to us, we're looking at supposedly two mirror images of each other. So like if I was looking at it, the first step I would do to get to the second one is do this.
That's not a mirror image, you just flipped it over. So you're looking at the same molecule if you do it that way. You actually need to build it backwards. If you're gonna, so, and this is where the models actually might slow you down. You do get extra time. So it's one way to do that, but you might also run out of carbons if you try and build the entire thing every time.
Sorry, this looks better. And you give me. So then how did you flip it back?
The way that I did it in the problem here is I said, okay, I'm gonna take this whole thing and I wanna put this big long chain that I circled, I wanna put it back up and to the right the way it was. And in order to do that, I had to take it, I guess you could do it like this, where my thumb is gonna be the hydrogen that's not shown. And my middle finger is the big chain, this is the methyl. If I do it like that, now the big chain is back where I want it. The methyl is sticking out towards me now, and the hydrogen is into the board. And then so when I redraw it that way, I get this.
You get them both coming towards you now.
They're both coming towards you. They both were away from us, and now they're both coming towards us, so both stereo centers flipped.
So it's not the new vocab.
It's not the new vocab word. It's, if they both flipped, then it is the mirror image of what we started with, which makes it an enantiomer. Enantiomer is mirror image, distereomer is not the same molecule, but not a full mirror image. Usually means you flipped one of the stereo centers, but not the others. And the way that that's gonna show up on the test is questions just like that. Here's two drawings. Are they enantiomers? Are they diastereomers? Are they constitutional isomers, which should be the easiest to recognize? Or are they the same molecule? Constitutional isomers are the easiest because that actually means something's attached to a different carbon, not just a mirror image or something like that. And so that one, that should be really straightforward. And so like I said, I'm not gonna promise there's gonna be one of each of them. But there's 4 options and 4 problems. It would make a lot of sense.
So then the enantiomer is achiral.
The enantiomer is also chiral.
But it's a mirror image, one's flipped.
If it's a mirror image, then you have 2 different molecules that they both are chiral. They're chiral in opposite ways.
What? It is that because it's a mirrored image with the chiral centers all chiral centers were flipped.
Exactly. All right, we're gonna work on this as practice in lab.
Yeah.
So the last thing I wanna say before we'll break a couple minutes early even to let your brains reset and take care of the things you need to over lunch. Last vocab word associated with this. Meso. Like the soup. We'll pronounce it that way anyway. If you have chiral centers, but your entire molecule has a mirror plane in the middle of it.
Oh, you mentioned this.
I have. If there is a mirror plane in the middle of your molecule, and that means when we flip both of those stereocenters to find the enantiomer, we actually get the same molecule back. Because if we flip this so that both of them are pointing down, we can actually take what we started with and just flip it like a pancake to get the same molecule back.
Yeah.
So even though it looks like we do have two chiral carbons here, the entire molecule is not chiral because it has that internal mirror plane.
Yeah.
So anytime you can see that it's the same on both halves of the molecule. Like for instance, even if we just had something like, even if it's just this molecule. If we took the mirror image of that, it would be the same molecule. Because the whole, so it would be a little bit like if your hands were perfectly symmetrical. If you had two thumbs, if your pinky was another thumb, you can't tell your right hand from your left hand anymore.
You'd have to have perfectly straight fingers.
You would also have to have perfectly straight fingers. But if you think about that, one of the ways that we can tell your right hand from your left hand in a picture is that you can find top and bottom, you can find pinky and thumb relative to each other, right? If thumb and thumb are symmetrical, then all of a sudden your hand is not chiral anymore. Now all of a sudden you can't tell the difference between your right hand and your left hand. There is no difference. Right, so that would be a meso compound. Meso compounds look really symmetrical because they are. So this version doesn't have the internal mirror plane. Because one's up and one's down. If you reflect it, you get one down and one up, but they're reversed.
Yeah.
Those are enantiomers. If they're both up and they're both the same thing, when you reflect it, you get the same thing back, which is what makes it meso. Right, so that's the last piece of this problem. If I give you a compound that has an internal mirror plane, it can look like it's an enantiomer, but as long as it has that internal mirror plane, it's really the same molecule. And that's really splitting hairs. That's like the toughest concept, not the toughest concept, but like the last needle on top of the haystack. No, what's the phrase? Straw on the camel's back.
Got it.
That's the straw on the camel's back. It's not that tricky in and of itself, but piled on everything else, it is a lot. Let's end there for now.
Yeah.
And then we're gonna talk about energy for probably about 20 minutes, maybe half an hour of energy stuff. And then the rest of lab is just review and practice problems for as long as you guys can take it.
Okay. I saw you made an announcement about it already being ready.